For today's presentation, our group would like to talk about the pirate, uh, Acropolis of Athens. And our group is formed by Chelsea, Eddie, Teresa, and I. And here is our project introduction.
Okay, first we will talk about our motivations. So why we any natural disasters, including seismic activity, accident and pollution that can corrupt and damage many history natural activities. Earthquakes are one of the most common phenomena. So why we choose a partner as our object? Because partner is a symbol of classical spirit and civilization. Uh, uh, we should protect those uh, structures because it's important for our history. Our objective is first we will analyze the stability of partner under natural disasters. Second, we will perform a mesh independent study to verify output. Third, we discuss the restoration of the roof with optimal materials.
And here I'll talk about the background of our structure. The Parthenon, one of the most iconic monuments in the Acropolis of Athens, remains a historically and culturally significant structure in the world today. The Acropolis of Athens, meaning high city or city in the air, symbolizes the civilization and classic art of ancient Greece. The structure of the Parthenon was chosen due to its stunning complex, universal symbol, and seismic resistance. The construction of the Parthenon started in 447 BC, ordered by the Greek statesman Pericles. The two architects, Pictinus and Callicrates, built the structure, and the sculptor Phidias was responsible for designing the historic style temple. The Parthenon, made almost entirely of Pentelic marble, is separated into four zones: the crepida, the colonnade, the entablature, and the roof. Measured from the top layer of the step, the dimension of the base is 69.54 by 30.89 meters. Above the floor, the Parthenon has 46 outer and 19 inner pillars. The average height of the pillars is 10.43 meters, and the average approximate diameter is 1.93 meters. Each of these columns is made of around 11 drums or sections that do not have the same size. As you can see the picture on the bottom right, each column is not made of a single piece of marble, rather multiple pieces stacked on top of each other. The Parthenon is purposely made to be a structure with imperfect angles to produce a straight and perfect frame for the human eye from a distance. The structure's careful design and construction, including the columns and the marble slab sections, allowed the Parthenon to stand for centuries. The building was known and studied for its resistance to the abundant earthquake activities around Greece, and the building remained complete until 1687. This year, during the Mauryan War, the Parthenon was severely damaged and destroyed, sadly by the impact of an explosion during the bombarding of the Venetian army. A cannonball struck the interior of the structure where the Ottomans stored gunpowder. After this event, the restoration of the Parthenon is being investigated and improved until today. The focus of this study will be on the dynamic analysis and response spectrum of the Parthenon using ANSYS. Through the finite element analysis, the results can be used to conclude the stability of the structure and be further investigated for future implications and restoration.
And here is the geometry as the input for our model. And the model is shown here, and this model has the 85% of the originality of the real structure. And I like to talk about the methodologies here. for the natural conditions. And for the material database, we only have two materials. The first one is the limestone, and the limestone is in the database in ANSYS. And what we do for the Parthenon marble, we insert the properties for it, and the material properties are shown here. And we firstly conduct a static analysis. To perform this analysis, we analyze the self-weight of the structure in ANSYS workbench. And firstly, we insert the static structure analysis and insert the material properties and geometries. Then we mesh the geometry, and the element size is set as the default in the first mesh. And then we modify the mesh size for verification purpose later. And then we insert the standard Earth gravity and fix the bottom surface of the platform on the ground. And no output is necessarily needed to be acquired from this analysis because it serves as a setup for all following analysis. And from this setup, all the models are pre-stressed by self-weight in later analysis, and two manners of mesh are adopted.
我没有听明白你的意思，请再说一遍好吗？
Sorry, my series. And in the static analysis, I like to talk the mesh here. This is a default mesh, and you can say it's pre-curves. And for our user-defined mesh, we come up with this mesh from the first analysis. We figure out that the columns have the most deformation and the stress. So we reinforce the mesh here to check the activity on these columns and the plate. And for the natural frequency, we analyze the model for the structure, like the model analysis. And we firstly connect solutions of static structure analysis to setup of model and mesh the if we do this setup, the mesh and geometry are not required again, and the structure is pre-stressed by self-weight, and the boundary condition is same as the previous one. Then we set the maximum modes to find 6, and the output from this analysis are 6 modes shown here, and extra equivalent stress. And the model analysis serves as a setup for following 3 analysis, because for the response spectrum, the harmonic response, it's just a superposition of this natural frequency model. And for the harmonic response, the analysis of the structure is under harmonic loading. And we just repeat the step, and in the analysis setting, set range of frequency which we are interested. It's from 20 Hertz to 37 Hertz. And we insert a harmonic acceleration from the ground in Y direction to mimic, to model excitation from the ground. And the output are total deformations. For the response spectrum, we analyze the structural response under a certain spectrum. And we just repeat the steps and insert a certain spectra, and which named R as acceleration in ANSYS. And we generate the artificial accelerogram and the response spectrum in a software named Seismoartif. And the outputs from this analysis is the deformations. This deformation includes 1 total deformation and 3 directional deformations, and then extra equivalent stress. How to generate the earthquake accelerogram and response spectrum? We firstly set up a target spectrum based on the Eurocode 8+3 and select what we want. And this is the elastic spectrum, and earthquake type is type 1 earthquake, and the ground type is form of hard soil, which is B type. And the importance class is 2. And the damping ratio is 5%. And Then we analyze the real accelerogram and generate the accelerogram and spectra. And this is time series we generated, and here is the corresponding response spectrum. And you can see here the dependent variable and the independent variable are not what we want, because if you want to insert this data into ANSYS, you have to have your x-axis in hertz and the y-axis in meters per square per meters per second square, and we just do the unit conversion in the Excel. And here is the results and discussions.
So we will be first discussing the results of the natural frequency in ANSYS, which we obtained output for 6 modes using static structural analysis and modal analysis. So in the first mode, which is the torsional mode, the structure is twisted. And you can see here the maximum deflection is 0.004 meters at the connections between the corner columns and the roof support. So if you look at the animation, you can see the red area where the maximum deformation is. It's at the 4 columns near the plate. And to verify our output, we created a new user-defined mesh. And here, as we said, we refined the mesh for only the columns and the plate between the columns and the roof, since this is where the deformation occurs most. So it is also unnecessary and inefficient to refine the mesh of the entire structure. And the result obtained with this refined mesh is 0.0039 meters, also at the same connection between the corner column and the roof. And you can see that the result is almost very similar, which helps to verify our result.
Then we simulated mode 2 of natural frequency, where sideway movements occurs along the longitudinal direction, and by default mesh, the maximum deflection is 0.00025 meters at connections between corner columns and the roof support. And as we refine the simulation with user-defined mesh, just as what we did for mode 1, we got the same answer this time as the default mesh, and thus the solution is verified.
In mode 3, a similar side sway movement is analyzed, but in the transverse direction, or also known as left to right, and the maximum deflection is 0.002 meters, also at the connections between the corner columns and the roof support. But in this mode, the deformation is spread along more exterior columns, especially on the 2 narrow sides of the structure. And this is again verified with the refined mesh, and we obtain nearly the exact same output.
And here for mode 4, the structure is bending, as you can see in animation, and the maximum deflection is 0.001 meter on the corner columns. And when we refined it with user-defined mesh, again, the maximum deflection is 0.00089 meter on the corner columns, resulting in only a 0.00011 meter difference, which is negligible enough for us to determine that the solution is verified.
And in mode 5, symmetric buckling, which is basically applying a compression downwards on the structure, is analyzed. And the deformation is 0.003 meters. And you can see in the animation that it's almost entirely on the corner columns. And next. And the refined version is not identical, but has a very similar value. And you can see the area of deformation is also around the same.
And for mode 6, the columns buckle in an anti-symmetric fashion, As you can see in the animation, that the columns are pressed to bend to the same direction instead of like opposite to each other as 1.5. And the maximum deflection here is 0.003 meters, still on the corner columns. And then we verified again with user-defined mesh and got the maximum deflection is 0.002 meter on the corner columns, which is close enough for us to say that the solution is verified.
So here we have our results for the harmonic response, where we applied a harmonic load in the y-axis, or from the base and the ground to the structure. The maximum deformation is around 0.0019, and the columns, you can see they're oscillating as they deform, which corresponds to the harmonic aspect of the load.
And in the same sense, we use a user-defined mesh model to check our answer and gained very similar results from the default mesh one. Therefore, we can say that the solution is verified.
And here are the outputs we got for the response spectrum, where we added an earthquake excitation from a software onto the structure. And the value of the deflections are very small, which shows relative stability. And the total maximum deformation you can see is only 2.86 times 10 to the power of -6. But if you look at the animations or the pictures closely, it is also evident that you can see the maximum deformation is still on the corner columns, and especially in the center of these columns.
Then we continue to test the von Mises stress through response spectrum, and the maximum equivalent stress is 14855 Pascal. We want to mention that we do not know the maximum stress of each column. Therefore, the maximum stress in general could differ according to the performance of individual columns in reality. The number 14855 Pascal roughly talks to the middle of the corner columns here.
And here's just the refined version of the response spectrum. And the results are not identical again, but they're nearly the same, especially since these numbers are very small, like to the power of 7 and to the power of -6.
And here's a verification of the von Mises stress. According to the refined meshing, the maximum equivalent stress is 13306 Pascal, which is very close to our previous answer.
And here's just the chart which we compared the values we got for the default mesh and the user-defined mesh. As you can see, the numbers differ by a very small value, which is why this is the mesh independent study, and it shows that changing the mesh will not significantly change our output. And so what we want to discuss is that the results obtained is the most vulnerable part of the structure is the marble column. As you saw in the previous animations, the maximum deformation always usually occurred on the columns, and especially the corner columns. So this gives a hint that during future restoration processes, architects should take into account checking the conditions of these marble pillars. However, actually in reality, the columns were built in the corner to have a larger diameter by the Greeks, and this may have been due to the fact that it would be more stable to withstand stress during seismic activity. And we also wanted to discuss two proposals for the restoration. The first proposal is to not take any action, which currently not many major restoration projects plan on fixing the Parthenon back to its original state due to failure caused by using materials that have further corrupted the structure. But another proposal is to add a roof made of e-glass FRP, or fiber reinforced plastic. And we think this is an appropriate material due to its chemical stability and low density that makes it least likely to damage the building as much as others. And its appearance can also easily replicate the original structure by painting it. However, after conducting static structural analysis on the building, the previous proposal did not seem to work out because after the addition of an FRP roof, the deflection due to the self-weight increased significantly, which would likely cause even more damage to the structure. And you can see the results of these simulations below. So to summarize, in this project, a similar structure to the Parthenon in the Acropolis of Athens was modeled and analyzed with ANSYS. And we got outputs from 6 modes of natural frequency, evaluated the harmonic response, evaluated the performance of the Parthenon under earthquake excitation, and finally tested the viability of restoring the roof. And the analysis modes we used in ANSYS for what we did above are respectively static structural analysis, modal analysis, harmonic response, response spectrum, and explicit dynamics. And to test if these results were reliable, we used mesh independent study by first using the default mesh with an element size of about 3.5 meters. Then we refined the mesh for the columns and the plate to around 0.5 meters. And we compare and the size of the roof to 3 meters, and we compared these results with the previous results, and the values were nearly the same, which shows that the result is independent. And we also compared with other research papers and trends that show the same pattern. For example, another research paper on seismic activity in the Parthenon actually states that there's also a stronger deformation in the columns. So in conclusion, as we discussed, the columns, especially the corner columns, has the most deformation. And these results correlate with the fact that the corner columns are built with the larger diameter. However, future maintenance should still be done on the structure and the columns. And lastly, after doing static structural analysis, we also found that it is impracticable to restore the roof due to secondary damage.
And here is the tension for man-made damages. And as we presented before, a bomb just hit the chamber inside of the arsenal, and the chamber was a powder magazine of Turkish, and the blast took place inside of chamber, and the roof just gone. And the chamber is modeled as the TNT in the simulation in the explicit dynamics. And here is just some animations for the explosion. The result is not verified, but it's just shown here. And the maximum displacement of the roof is 4 meters away from its original place. And state amount contributions. And in our group, everyone get evenly distributed work, and they work on the part they are interested in. And here is our reference page. Thank you.
Very nice presentation again. Any questions from the audience? Are the corner roofs the same size in your model?
Yeah, we model the same size. We didn't like change the size for the column for the corner columns. Like if we change the size, we cannot see the result we expect, because like for example, the maximum deflection occurs on the corner columns. If we just enlarge the cross-sectional area of the column corner columns, we may not see that large deformation and stress concentration. So we just keep the same size as other columns for the corner columns.
the ruins of the Parthenon, do you see any significant difference between the sizes of the columns, corners, and interior? I wonder if the size difference is significant.
I believe it's significant, but we just didn't change the size because for like simplicity of the model.
Yeah. Now I know that this is a computational mechanics class. It's not a structural mechanics class, but just to explain the vibration modes, not only of the Parthenon, but also of the Golden Gate Bridge, as well as the Petronas Towers. The main fundamental mode of vibration is the vibration corresponding to the direction at which the structure is the softest. It's true in Petronas Tower. The vibration in the forward direction of the tower, parallel vibration, perpendicular to the bridge, comes first before the left and right, or what Chelsea called earlier as the transverse direction, because in the left and right direction, you have the effect of the bridge. Same thing with the Parthenon. The most fundamental mode, the first fundamental mode of vibration, I believe, is the twisting mode, isn't it?
Yes, it is. The Parthenon is not very torsional stiff. So the first mode is the torsional mode.
Because that is the direction where the structure behaves the softest. Now there are two sideway modes. One is the forward mode, the other one is the left and right mode. And as we saw from the results of their analysis, the forward mode is more critical because it is softer in that direction than in the transverse or left-right direction. So that's just a food for thought. Those of you who don't have structural mechanics background. Interesting to see columns look like they're dancing in the buckling mode. That's a very interesting vibration mode. Any other questions? Come on, you guys, you should ask questions. This is not for the professor, it's alone. It's also for the TAs and for the audience. Any questions for the presenters? Okay, so no question. I am going to stop here. We'll pause for another 5 minutes. And then when we come back, we'll hear from the Golden Gate group.